Hello, welcome back to the MCAT grind. We have the last chapter of General Chem, also my least comfortable one, and I think now I'm a little better now with the concepts. So beginning with a review of oxidation and reduction. Oxidation is basically losing electrons, and it happens in a galvanic cell. A galvanic cell is the general term for batteries, in which one side split into two half reactions, and each side, just like how we split the two half reaction, one side undergo oxidation and another side undergo reduction. Oxidation, the site is always at the anode, and the reduction site is the cathode. You can remember by N, ox, as well as red cat, associating with each other. Now, at the anode, the solid part, for this instance zinc in this Daniell cell, the zinc solid will go into the solution by losing the electron. You see how it's neutral state, 0. By losing electron, it turns into the zinc ion, and the lost electron will travel here, driving this battery into an electromotive force and doing work, finally arriving at cathode, which these electrons attract these copper ions into plating onto here. And this plating process is basically called galvanization. And by plating onto here, they turn from copper ions into copper solid onto here. And if you let this process go on and on, this side eventually will lose so much electrons, it will just turn positive. So what happens is they put a salt bridge here, usually like a salt that doesn't react with the reaction itself, such as KCl, which the Cl ions will then come here and trying to neutralize the buildup of positive here using the negative here. And the opposite happens where the potassium tries to neutralize the negative buildup on this side. So by drawing out into equation format, zinc solid will go ahead and oxidize into the zinc ion, and on the other side, split by the two lines, the other side of a beaker will have the copper ions reducing by gaining electrons into the solidifying onto the cathode plate. This is all to drive work, and hence this is a spontaneous reaction. It will happen by itself and generate energy. Electrolysis, on the other hand, is non-spontaneous. It requires energy input to drive the process. So usually it could be used in chlorine gas formation, and also just the dissociation of compounds, such as H and H2O. So one side, anode again, will still have oxidation happen, but this time the oxygen anions are attracted to it, because electrons always travel from anode to cathode, and when they come onto here, they're attracted to the positive overall side on the anode. By driving electron this way, it generates a positive point here on the anode, and hence the relatively negative ion in a compound will be attracted to anode, and a relatively positive ion in a compound in H2O will be driven to the cathode, where the negative have been built up here. So opposite to what galvanic cell, the anode here is positive, whereas the anode here is negative. Right, this net positive will allow all the negative anions to come onto here, and just like here, where the salt here is Cl, negative anions come into the solution here. Now, there's a certain ways to see based on equilibrium. The net E, electromotive force of the cell, will be positive if the K equilibrium is more than 1. If the K equilibrium is less than 1, then it will be a non-spontaneous reaction. K equals 1, then there's no net change in spontaneity. We can use Faradays to calculate this. 1 Faraday is about 10 to the 5 coulombs per mole of electron charge, and we can say that it's hard. calculating a mole of metal, its IT is not fun, right? I is a current, the current usually in amperes, T in time in seconds, so if it's in hours, you need to change that into seconds. N is like the electrons, number of electrons in a solution, so if it's like dealing with net 2 electron change, like zinc and copper, then you write 2 here. F, just put 10 to the 5, so you can see how much mole of the metal is being used, and you can use that to convert into grams of copper being plated onto the cathode. To do any sort of net additions to see what's the net EMF resulted from this reaction network, you can use this from the the cathode side usually is positive, and subtract the negative side, which is negative, so you end up with a greater number. Basically, you're looking for the difference between the reduction potential. The more negative the reduction potential, the more likely it's the oxidation. So if you have 1, that's zinc, it will be like negative 0.5, and it was a copper 2 plus here, it will probably be like positive 0.5, because zinc wants to lose the electrons and copper wants to gain the electrons, right? You can also calculate delta G, the net Gibbs free energy, by using negative n, number of electrons, multiply Faraday's constant, 10 to the 5, and multiply by the electromotive force of the cell, the net E of the cell. You can also use this equation to calculate any change in the new E cell depending on the current equilibrium of the position. If the equilibrium has changed and it's not 1 anymore, if it's, let's say, 2 or 10, if there's like way more products than reactant, 10, and that log would be 1, so negative 0.06. Minus that, then by having more and more product, the E cell is going to decrease and decrease. So basically, as the battery runs over and over again, over time it's going to reduce in the force and the power. That's why the battery running over and over again will lose as much power. Okay, that's pretty much it.